Geometry is where we input our data for the wall, for what we want it to design with. Let me slide this over so we see the whole screen. The height is going to be from the top of the leveling pad to the top of finished grade. The program designs to grade, not to blocks. The blocks are inserted over the face to get our best match. So that's what we're looking for. The exposed height is going to be from the finished grade in front of the wall to the top of the wall. In this case, we have 8 inches of embedment. We have a 5-foot high wall. We have 4.33 feet exposed. The batter, these are pre-programmed also. The CornerStone 100 has a 4.5 degree batter, which is the setback per unit as we go up the wall. Embedment is depth below grade. The minimum is 5% of height for a level toe slope, a 3-to-1, 5% H over 20. A 3-to-1 toe slope will be H over 10. A 2-to-1 toe slope will be H over 7. This program does not design embedment for toe slopes. That information has to be input by the user. So we're going to with 6 inches there. The depth of the leveling pad is 6 inches. The width of the leveling pad is 6 inches in front of the unit, 6 inches behind the unit. Slope angle is the slope above the wall. 2-to-1 slope, 26.6. The horizontal distance from the back of the block to the top of the slope is shown there. We can come in, and if we make that 50, that's an infinite slope, meaning that the failure plane goes beyond the break of the slope, which is interesting in here because the red line over here is your theoretical failure plane. There's your slope angle. When we come back down here and we say that our soils are 28 degrees, our slope angle is 26.6. Those angles are almost together. And if we do an infinite slope analysis, we're going to find that that slope is unstable. If we look at a reinforced design, what's happening is there's your slope angle, there's a failure plane, they almost parallel. And if we look at a gravity wall design, you can see our KAs, our active earth pressure coefficients, are getting very large. We do the same thing in geometry. We say we have 0 slope. Gravity wall design, the failure plane is much steeper. It approaches an angle of 2 vertical to 1 horizontal, roughly 60 degrees. And our Ka values are much lower, around that 0.3 range, 0.25 range. Reinforced design will give you the same thing. So that's the relationship between the slope angle and what we see, what we're designing for. We can also have a slope angle of 3-to-1, 18.4. We can put a 2-foot offset in there. And when we do our design, the slope is offset. We're now into a trial wedge mode because the failure plane is going beyond the break. And our Ka values are much lower at the top because the failure plane is now going into a horizontal surface, and then it gets toward the bottom where the failure plane is going to the slope. Our Ka values are increasing. We're seeing more of that area of the slope in the failure zone than we did the upper part of the wall. Reinforced, we don't see the Ka values, but we do see more load on the geogrid as we get to the bottom. Another way to look at that is we'll leave our slope angle as 0. we'll put a live load in here of a highway loading 240, zero offset, a width of 50 feet. Do a gravity design. There's our surcharge. You can also see now the overturning is controlling from the second block down. We go to reinforce design. Our T-max values are larger. Put 0 in here, reinforce design. Our T-max are 68, 160, 141. We put a live load in there. Reinforce design. We went from 60 to 230, a lot larger. Come in here and now we move that offset back 3 feet. Do reinforce design. We're only picking up 70 pounds of earth pressure. We're not picking up any live load on the top 2 layers of grid because the failure plane isn't extending into the live load. For the bottom grid, we do start to pick up a live load in there. And as we move that load closer to or further back away from the wall, we can see that our live load contribution increases. The failure plane will search until it finds the largest value. It's going to keep moving back. If we have a large live load, which is offset from the wall 10 feet, you see there is no contribution to live load. The live load is well beyond the failure plane. Anything that loads the wall would be in this zone up here. If we look at our image on global, our load is back there. It's not even going to affect the external stability. So we see a lot by moving that load back and forth. These are live loads. By definition, a live load is a transient load, such as a highway load or automobile loading. We have a driving force, but we don't have a resisting force. We go back to 0 offset on this. A reinforced design. Let me move this over. Anything within the grid zone does not have the resisting force. When we look at sliding, if I go to my global, if I look at sliding, this whole mass sliding forward, this load is going to provide a driving force. This load is ignored as a resisting force. Grid seem awful long, but let's not worry about that right now. When we go into a dead load situation, a dead load, 0 offset, 50 feet wide, a dead load is considered as a resisting force. So that dead load is going to apply resistance to sliding. The dead load will also apply a driving force. The two balance out, or the two both apply forces. If we slide this back over, we have one dead load, we have 2 dead loads. We do a lot with railroads and live loads, so we can have one load as, say, the railroad loading, the other loading as the sidewalk or a road. We can have 2 different loads in there. We'll leave that. If we go to toe slope, we can say we have a 2-to-1 toe slope that's 5 feet long and 0 bench width. Slide this back over. Do reinforced design. There's our toe slope. By global, I can see the bigger picture. There's what we look at. In a static analysis, when we look at sliding, overturning, bearing, toe slope does not influence the results. We are simply looking at this body resting on a block of soil. Where we do see the impact, we go back to static results. These numbers won't change with the change in toe slope. We go to global. Now we look at toe slope. We've got a 1.12 factor safety. If we look over here, we want to see a 1.3 or greater in that. If we go to a 0 toe slope, update design. We can do that with the yellow button up here. We go to global. We're at 1.45. That slope is stable. So you can see as we start to increase that toe slope, our global stability starts to decrease. Toe slope angle 18. Now we'll take it a long 20-foot slope down there. We update the design. See our slope coming down. We check our global, 1.17. That doesn't meet the factors of safety. Two things you can do. One is you can lower the structure to embed it deeper. These geogrids will drive that failure plane deeper, or we can make our grids longer. These were 5 feet, 1.17. We go back to static. Push those out to 8 feet. Whenever you make a change in this, the calculations automatically update. We'll go to global, 1.31. Now we're stable. In cases where you have a large toe slope below the wall, we need to look at global. We need to make sure that we're up in that 1.3 range or greater. Embed the wall deeper, make the grids longer. Two choices. The other choice, obviously, is we go to reinforced design, and we said that our global was less than 1.3, 1.17. The other thing is if you're working with a clay soil or a silty soil, there's a very good chance that you're going to have cohesion in there. These numbers will go up a little bit, but now we look at global, 1.39. In most cases, there will be cohesion in the foundation, especially if it's a native soil. It's not been excavated, replaced. Any kind of a silty soil, a clay soil, again, will have cohesion. That's up to the geotechnical engineer to define, what's a reasonable values for the soils you're designing for. So, a couple options on global. Cohesion, increase the grid length, increase the amount of embedment. By increasing the amount of embedment, obviously your wall height is going to go up. So we've talked about live load, dead load, toe slopes, slope embedment. These numbers don't impact the design, but what they do is you'll notice that this box down here is yellow. If I said I had a 0 toe slope, it goes back to a beige color. Once I put a toe slope in, I pop out of it, it's just a warning that you don't meet the requirement. The suggested embedment for that wall is 1.3 feet. Given that toe slope, given the wall height, to meet this embedment down here, which would be a 2-to-1, h over 7 says you need 1.3 feet. So just a hint down here that maybe we need to look at this, maybe we need to adjust those. Last items, minimum length to height ratio. This is for a reinforced wall. NCMA has a 60% base to height ratio. That is for grid length defined from the face of the wall to the tail of the grid. If I were to go to an AASHTO design, AASHTO design is 70% from base of wall, from face of wall to tail of the geogrid. So that's going to be 8 feet. And if we look a little further, AASHTO defines embedment as measured from the tail of the block to the end of the reinforcement, 0.7H measured from the tail of the block. So it'd be from the tail of the block to the tail of the geogrid would be 70%. AASHTO also has a minimum grid length of 8 feet. NCMA has a minimum grid length of 4 feet. Four feet is simply from the front of the block, typically a foot, another 6 inches to a foot. 4 feet gets the grid beyond the failure plane. So we have enough embedment where we're actually getting some lock into the soil. Maximum grid spacing is 2 times the depth of the unit. So our units here being 1 foot deep, the maximum spacing is 2 feet. If we wanted to reduce that to 2 block spacing, we could say 1.5 feet. We do a design and it will place the grids at maximum of 1.5 spacing. Helps do the layout. If we put that there at 10 feet, and we do reinforced design, it doesn't matter. The program was always going to default to 2 times the depth of the block, regardless of what that number is. We can always come in here, delete a grid, and it's saying that design, we get a factor of safety of pullout on the upper grid. 1.16. Let me get rid of that dead load and get rid of that grid. And I still fail on pullout on the upper grid. But it would say that even though with a wider spacing, the wall would work. So this will work at 2 block spacing. I think that takes care of this. We do have one other. If we go to options here, we have, what am I looking? I'll show allowable bearing and show partial coverage. So these are 3 options that I leave turned off, but we can turn those on. And what it says, if you go with a block that uses partial coverage of geogrid, say the Magnum stone, we can put through the core 2 foot wide pieces. That would be 50% coverage on the top and the bottom, 100% internal. We can reduce the percent coverage, run a calculation. If we look at static results, our tension's 120. If we update that with 50% coverage, the Tmax didn't change. Oh, it's 100% coverage. Let's go back here. Percent coverage. Well, let's see. We can do it this way. Percent coverage, 50%. We can see that doubles the Tmax in the geogrid. Allowable bearing. Many times a geotech report will come out and say the allowable bearing is 3,000 pounds per square foot. We can input that here. It doesn't do anything to the calculations, but what it does, it shows the allowable bearing of 3,000. If your applied bearing is over 3,000, it would show you a flag as no good. So it becomes just really an indicator flag down here. I think that was it. Percent coverage, allowable bearing, cap offset. We don't use that very much, but say the wall was 5.5 feet tall, reinforced design. We designed to the grade line. We place the blocks to fit the face. In this case, the full-size block is too short. The cap block is too high. We fall right in the middle. We could go to geometry, cap offset of 4 inches, do a design. Yeah, maybe 5 inches. Well, what it should have done is, I think if we go up to 6.5, there we go. What it does is it lets the soil extend beyond the top by that cap offset distance of 6 inches, 4 inches. If we come back and we say, yeah, my default is 1 inch, it's going to throw some more blocks on top. So that's the option to play with how much block you've got setting above grade. The NCMA program, SRWell 4, they designed the block heights. We can do that in this program if that's your preference. Force height to block height. We can come back in here. We've got a 6.5 that says the block height is 7. As you exit out of there, it's going to change it to 7 feet. We come back and then we change that to 5. That one works. If we change it to 4, and if we just exit out, it's going to change it. So your grade is always me. If that's your preference, you can change it in preferences. I don't. I want it designed to where the soil load is, not to where my block is. Cut angles, cut dimension over here. If we put that in, what that does is it shows a distance to the cut line. We're going up to the failure plane externally, or what we said it was 2 vertical, 1 horizontal. So it's 8.2 feet from the face of the wall back to where that cut would be. Good for the contractor to know how far behind that wall he's got to cut. We can put a parapet on the wall. I say I want a 4-foot parapet. I'm going to make it 1 foot deep, and I'm going to say it's concrete, so it's 150 pounds per cubic foot. I do a reinforced design. There's my parapet. Whoa. He says with that load on top, that wall at 4.33 is going to work as a gravity wall. Makes sense. Let's go to a 10-foot high wall. Now it's reinforced. What the parapet does is it adds weight to the wall face for the sliding and overturning calculations. Even in a gravity wall design, it's going to add weight back here to help with our overturning and moment. You can see here that can't count the blocks, but we're up 4 feet as overstressed out of a total of 10. So we've got a 6-foot high gravity wall with that on top. Not where you want to go, but that's what it's doing. So that's the parapet input down here. We've already talked about the warning flags, MSE. I think we're good on this page.